All right, I wanted to try to record a quick video about the NMR for this week's product. It is pretty involved. There are 22 protons, 22 hydrogens in this molecule, so that's quite a bit. We've worked our way up to the most complex NMR yet. I have a sample printout here from the 90 megahertz machine. The 60 megahertz was similar. So on the 60 megahertz, it was a little bit difficult to resolve the quartet. It was kind of blending into these other signals here. Okay, so I've kind of color-coded these protons on the molecule. These purple ones are all aromatic protons. So let's get purple around 7 to 8 ppm usually. So we're talking about this area over here. And then we have two different kinds of benzene. We have this para-substituted. Remember, when we have the para-substituted, these two are equivalent. And these two are equivalent. Basically, we can look at one side of the molecule, and the integration is just going to be twice as big because there's another set of the same conditions on the other side of the ring. So we have, if we call this A and this B, then this proton would be a doublet because there's one neighbor getting split by B. This proton would also be a doublet because it's getting split by A. Those are the only two neighbors. These two carbons do not have protons on them. So these two are just neighbors to each other, like the only two people living on the street. They're each neighbors to each other. So we have a doublet and a doublet. But then since we have the same situation on the other side of town, we have two copies. And so the doublet for A integrates for two protons because we see it twice, and then the doublet for B integrates for two protons because we see that twice. This particular doublet, we were not able to get out of this mess, so I don't have it called out separately. This one was far enough away that you were able to see. So you can see the two doublets being worth different, two each. They're each worth 2. So probably I would think that the B is a little bit further upfield because it's closer to the oxygen. I'm not 100% sure about that, but that was probably B and probably A, but maybe, maybe they could switch. I'll put a little question mark here. They're pretty close together though, and they're all in the aromatic region. This benzene ring over here, we have more complex splitting, and since there's not a lot of electron withdrawing groups or electron donating groups on the ring, they're all going to be in a similar area. So we have multiplets on top of each other. This one over here should be a doublet because of the neighbor, so we should have a doublet here. This one over here is split by this and by that, so it should be a doublet of doublets. This one over here should at least be a triplet because of the two neighbors here. So we have some complex splitting, and it's all on top of each other. So that's why for a mono-substituted benzene, we usually just kind of see a lump of peaks that are very difficult to resolve into doublets and triplets that they should be. So we have some more over here. Altogether, the 2 from B and the 5 from this entire benzene ring add up to 7. That's why we see a 7 integration here. The next proton that should be pretty high is a vinyl proton. Vinyl proton is normally 5 to 6. Remember, for the last compound that we saw, it was pushed up a little bit more into the aromatic region. It was underneath the benzene for the starting material for experiment 8. The product for experiment 7 had those vinyl protons pushed up a little bit further than 5 or 6, and this one does as well. We don't have something between 5 or 6. We don't have anything here, but we do have a signal over here that integrates for about 1. So we have 1H here, and it is a singlet. This proton over here does not have any neighbors. The next carbon over has a double bond to oxygen, no protons there. This carbon here has 4 bonds showing there's no protons there, so there are no immediate neighbors. So having it be a singlet makes sense. So we have that proton over there. Then we have green, color coding green is our next color, kind of going reverse rainbow here. We have protons that are directly next to an oxygen. They're on a carbon that is also bonded to an oxygen. So I've drawn those in green. So we have 3 hydrogens over here. That should be a singlet, no neighbors. The next atom over is not a carbon, it's an oxygen. There are no protons on it. So this should be a singlet. So we have a singlet worth 3. That is underneath here. There's some other stuff underneath here. So this is 3. I'll put the 2 in orange. So we have about 5 here. 4 of these orange ones that I've drawn, 2 over here and 2 underneath where this singlet is. That's why it's integrating for more like 5 when it should be 3. So the singlet is worth 3. You can tell there's something underneath the singlet that's not a singlet. We got some other signals under there, but the sharp singlet for 3 hydrogens is there. These other 2 hydrogens, they have 3 neighbors, so they should be a quartet. All right, not very easy to write, but it should be a quartet. That's what we see over here. I'm just going to put a Q. It integrates for about 2, so we have a quartet worth 2. We have a triplet worth 3 down here. So that would be these 3 over here with the 2 neighbors should be a triplet. Remember, a quartet that's further downfield worth 2, matching with a triplet that's more upfield worth 3 is the sign of an ethyl piece. So that is that ethyl piece over there, the 2 and the 3. That leaves these other 4 orange. Maybe I should have put a different color. All right, so that leaves these 4 that are unaccounted for. These ones over here, it's more complex than it seems. It seems like this should be a signal that's worth 2, but if you think about this as a ring, these are not able to spin around. So one of these hydrogens is next to a benzene ring. If this hydrogen were a wedge and this benzene were a dash, one of these hydrogens is a wedge and one of them is a dash. So one of these hydrogens is a dash, it's below the ring. One of these hydrogens is a wedge, it's above the ring. So if this benzene were pointed back, for one of the enantiomers, it would be pointed back. So it's next to one hydrogen, whereas these other 2 hydrogens are next to each other. So these 2 hydrogens are not in the same environment. They're actually different hydrogens. So we've already used up A and B. Let's call this C and D and E and F. So let's just say that these are C, D, E, and F. They are all different. So we have different ones. So this hydrogen is going to be split into a doublet by its neighbor D, and it's also going to be split into a doublet by its neighbor E. So hydrogen C would be a doublet of doublets. Hydrogen D would be a doublet of doublets. Hydrogen E has 1, 2, 3 neighbors that they're all different environments. So it's a doublet of doublets. So each one of these neighbors is different. It's like in a different house. So we don't have a house with the same neighbor, same house with 2 neighbors. We have 2 different neighbors. So it's like this E is living next to 3 different neighbors, and each of those neighbors is splitting it into a doublet. And so it's going to be kind of a complex multiplet, a doublet of doublets. F should be just a doublet. But the problem is that all of these are in very similar, locations. I had done some 2D experiments to try to figure out which proton is in which spot, and unfortunately, since 2 of them are kind of on top of each other and another 2 are on top of each other and underneath a very huge singlet, the signals in the 2D NMR that I was able to take are also kind of all on top of each other. So I have not been able to resolve which of these protons is which, but altogether these 4, we have C, D, E, and F. This is supposed to be a D. It looks like a B here. And then as far as which one is further upfield, that is a little bit more fine-tuned than we are able to do right now, because you can make an argument for anyone. This E is next to a benzene ring. H is next to 2 carbonyls. So you think that, this F proton is next to 2 carbonyls. So that one is probably very far downfield. This one that's on the same side as the benzene ring might be being affected by the electronics there. It's also next to it's an allylic proton. It's next to an alkene there as well, and this alkene is conjugated to a benzene, and so there's a lot of electronics going on over here. I'm not sure which of these would be affected more, the one that's next to the other hydrogen or the one that's next to the benzene ring. So in all honesty, I would have to look into this more to try to distinguish C, D, E, and F and figure out which one of these is which. I might do that at some point, but I think that this level of understanding of the NMR is probably more than enough for our first year organic investigations.